Are on chapter 5 here. I think we got a little bit into it last time. We were talking about equations and to balance chemical equations. So a reminder that when we balance chemical equations, we only change the coefficients. So again, those are obviously the numbers that come up in front. So we just put numbers in front of everybody to balance it. We never change any of the subscripts because obviously that will change what the substance is. And the goal here is to ultimately, as we talked about, end up with the same number of elements on each side of the arrow. The idea there is in a basic chemical reaction, really we're only breaking bonds and making bonds, and that's all electrons that are involved. There's no protons or anything like that changing. So we do have the conservation really of the elements as you go from the reactant side, which by the way is on the left-hand side of the arrow here, to the product side on the right-hand side of the arrow. And we just need to make sure that we have everybody with the same number on each side. A good way to kind of do a lot of balancing is to make like a little table. It oftentimes can help you sort of figure out where to start and where you need to kind of go from. When it is all said and done, there's really kind of two things you have to make sure of when you balance an equation. Pretty much you need to have all whole numbers as the coefficients. So they do have to be whole numbers. And it does need to be the simplest set of whole numbers. And again, what I mean by that is, as we may have talked about last time, if you went through and balanced some equation and you ended up with these as your coefficients, you could clearly go back through and divide everybody by 2, which would yield you in this case a plus 2b goes to 3c. That would be the correctly balanced equation. So, again, sometimes people will see maybe larger numbers to balance it, and it is technically balanced. But if you can't go through and reduce down the coefficients by a common number and obviously still hit a whole number on everybody, you should definitely do that. And that would be the properly way to balance the equation. Any questions on any of that stuff? Okay, so I think we're in the middle of some examples. So I believe we left off with this example here, I think, right? So why don't you take a minute or two and balance that guy up. Okay, let's take a look at this one. So like I said, it can be very helpful to make sort of a table, reactant side, product side. You kind of list all your elements there. So the boron, oxygen, and hydrogen. To start with, on the left-hand side here, we have 2 borons. On the right-hand side, we have 1. On the left-hand side, in terms of oxygen, we have 3 there, plus 1 more there, which gives us 4. Right-hand side, we would distribute the 3 into both of them. So that would give us 3 oxygens there on the right. And hydrogen, we got 2 on the left, and also, again, distributing that 3 in would give us 3 there on the right. So clearly in this case, boron seems probably the easiest thing to work with, but then erase it. We could fix that by putting a 2 in front of the boron here. That gives us 2 for the boron. For the oxygen, we now have 3 times 1, kind of bringing it in here. And then we also then need to multiply that by the outside guy as well. So that's going to be 3 times 2, which is 6. And the same thing will happen for our hydrogen, 3 times 1 coming in, and then also multiplying by the number in front would give us obviously 6 there for our hydrogen. At this point, we balanced the boron, but everything else is now messed up as well. The next really easiest thing to solve here would be hydrogen, as it's the only thing on one. It's in one thing on the left-hand side while we have oxygen and a couple things there on the left. So we could very easily go to hydrogen next and fix that by simply just putting a 3 in front of it. And that gives it actually gives us 6, and our 3 times 2 for the hydrogen there will give us 6. So hereby putting our 3 in front of the water, it was able to actually fix out the oxygen in this case, and we are obviously balanced at this point. Any questions on any of this? Yes, sir. Are we talking about the water here? So you want to do what now? So it like this, bottom right. No, we don't usually balance equations that way. The only time you'll ever see sort of something like that, if it's obviously not part of a formula for something, is sometimes when you calculate something like a molecular formula, they'll sometimes do that from like an empirical formula. We'll talk about it, I think, in a later chapter. But in balancing equations, it's always got to be in front. Those coefficients is really the only numbers that you should change. So you wouldn't never kind of bracket around something and do that. Or either I've seen people, kind of squeeze a big number in the middle, those two things. You don't do any of that. So just owning the number in front, everything else behind has to stay. If it started with brackets, you keep it, obviously, but you shouldn't add any of your own brackets. Other questions? Okay, let's try another one here. Let's give this one a go, balance it up there. Okay, let's take a look, see how you're doing on this particular one. So we'll start kind of the same approach. We'll make a little table. I got one nitrogen there on the left and one on the right. I got 3 hydrogens on the left and 2 on the right. I got 2 oxygens on the left. I have 1 oxygen on the right and 1 more there gives me 2 on the right. So in this case, it doesn't look too bad. We got everybody balanced except for hydrogen. So clearly that's probably a good place to start. In this particular case, we can't really just put a number on one side to get a balance. We actually have to go some numbers on both sides. And we could just look for the common number there, which is simply just multiply those two together. So 6 is sort of the common number that we could look for. That means to get my hydrogens to 6 on the left there, I will need a 2. To get my hydrogens to 6 on the right there, I will need a 3 in front of it. At this point, we have now 2 nitrogens on the left. Hydrogen 2 times 3 is 6, and oxygen is 2. On the right-hand side, we have still 1 nitrogen. Hydrogen 3 times 2 is 6. And now in terms of oxygen, I have 1 there, and I have 3 here, and that now is 4. So we successfully fixed hydrogen, but kind of screwed up everything else. So the next probably easiest thing to fix, as we can kind of see from this table, is really the nitrogen. Again here, nitrogen is kind of in one thing on the right, oxygen's in a couple of things going on over there. So probably very simply, we could fix the nitrogen by putting a 2 over here. By putting a 2 over here, it gives us 2 nitrogens. We got now our 6 hydrogens. Now in terms of oxygen, we have 2 in the first one, and we still have 3 in the second one. And that now gets us to a grand total of 5 at this point. Any questions up to there? So clearly we put some numbers all the way around. We don't want to kind of change those numbers. So really the only thing that we got left to work with at this point is really the oxygen there on the left. Now in this particular case, we need a 5. So we have 2 of them sitting there. So in order to basically get us to 5, we can use a fraction to help us do that. And we could use something like 5/2 in this case. That would then give us 2 nitrogens on the left, 6 hydrogens, 5 halves. 5/2 times 2. 2's cancel, gives you 5 when it's all said and done. So at this point, our equation is balanced. Is it correctly balanced? It is not. So this is a good example. It illustrates the point that sometimes you may need to use a fraction to balance the equation. But once you do that, you do have to get rid of the fraction because you do need all whole numbers. So what we would need to do in this case is multiply everybody there by the denominator, I think is what they still call that on the bottom. And if we do that, we're going to end up with 4NH3 plus 5O2 gives us 4NO plus 3 times 2 is 6H2O. And if I did that correctly, I should still be balanced. So on the left-hand side, now we have 4 nitrogens. Right-hand side, we have 4. Left-hand side, we got 12 hydrogens. Right-hand side, 6 times 2 is 12. Left-hand side, we have 5 times 2 is 10 oxygens. Right-hand side, there are 4 in the first one and 6 in the second one, which does give us 10. So we are balanced in this case. So you absolutely positively can use a fraction, and it oftentimes happens in this situation where you got like a diatomic element by itself, and then that guy's in a couple of things on the other side. A lot of times you might need to use a fraction. There is a very simple sort of formula to pick the right fraction. Pretty much the number on top is the number you need. So if you remember, we needed 5, which is why we went with 5. Number on the bottom should match the subscript. So if we look at the subscript here, it is a 2. So those guys should always match, and you'll always pick the right fraction in that case. Number you need up on top, matching subscript on the bottom, and that will get you the right sort of fraction every time. Any questions on that? Now, clearly, if you could just see the bigger numbers, you could go with the bigger numbers and, you could get a balance, but that oftentimes happens. Any questions on balancing there? All right, let's try a few more here just to see. Yeah, there we go. All right, so take a few minutes and balance these guys up and see what you come up with. Let's see how we're doing on these. Go back a page, write it up again. So we'll start with this first one here, which is C8H18 plus a O2, CO2 plus some water here. All right, so if we kind of make our table here, we got carbon, hydrogen, oxygen. Left-hand side, we got 8 of the carbon and 1 on the right. Left-hand side, 18 hydrogens and 2 on the right. 2 oxygens on the left. And again, here we have 2 in the first one and 1 more there in the second one. Gives us basically 3 for the oxygen on the right. Again, probably the simplest place to start here would again be the carbon, as it's all by itself over there on the right, basically, or in just one thing. We can fix the carbon very easily by just putting an 8 in front of it. When we do that, that gives us 8 carbons. We still have the 2 hydrogens. Now, in terms of oxygen, we do have 16 happening there with 8 times 2 plus 1 more there at the back end. So what did I just say there? That's 16, 17 oxygens at this point. The next easiest thing at this point would be to go to the hydrogen on the right. Again, I'm not going to probably hit the oxygen because we got it in multiple places on the right, 1 place on the left there. So I can kind of save that for the end. And to fix the hydrogen, we can do that by putting a 9 in front of the hydrogen on the right. That then gives us 8 carbons. 9 times 2 is 18 hydrogens. Now for our oxygens, we got 16 going on there in the first one, and multiplying the 9 over here gives us 9 more. So adding that together looks like a 25 situation happening at this point. Any questions so far? At this point, you could probably imagine maybe a fraction would be a good move here. So again, we don't want to change any numbers on the right. Otherwise, we're changing everything. So we can turn that 2 into a 25 by taking the number we need up on top. And again, a matching number on the bottom there will get us to the number that we need. That gives us 8 carbons, 18 hydrogens, and again, when you take 25 over 2 times 2, the 2's cancel and does leave you with 25 oxygens. Again, at this point, it is technically balanced, but not properly or correctly balanced because we still have the fraction. So we do need to get rid of the fraction. We're going to multiply everybody by the denominator there, and that's going to give us 2 of the C8H18. That will give us 25 of the oxygen, gives us 16 of the CO2, and 2 times 9, 18 of the H2O. And at this point, we now should have a balanced equation. We have 16 carbons on the left and 16 on the right. We have a lot of hydrogens there, so that is 6 carried to 1. We'll go with 36 and hope for the best. We got 18 times 2 should also be 36 there on the right. Oxygen should be a grand total of 50 on the left. We got 32 in the first one and 18 more. So 32 and 18 is 50 on the right. So we are balanced now. Any questions on that particular one there? So again, this is a very common situation where, fraction is very helpful. You got sort of a diatomic molecule, and then you got that guy in a couple of places on the right. Not always need to use a fraction in this situation, but again, that's a lot of times when maybe this situation does occur. Any questions on that? All right, let's take a look at the next one, which was something. It was, you had Fe to SO4 3 plus AgNO3 and FeNO3 3 and Ag2SO4, right? Okay, so when you look at something like this, you may not want to necessarily take the table approach, and the reason for that is if we take a peek, we do have a number of polyatomic ions on each side. So we got some sulfate there, we got some nitrate over here. And obviously, as we talked about with nomenclature, we have more than one polyatomic ion. You got some parentheses, a number on the outside. So, if you do go element by element, which in a table you can, you will have a lot of kind of multiplying in and keeping track of everything. So, you might sort of go a little bit wrong there. So a lot of times when you have an equation where you got a number of polyatomic ions on each side, and they're obviously the same polyatomic ion on each side, it's sometimes easier to just start with those and keep them as like units and balance them that way. So for example, here I got sulfate, I got nitrate. I'm going to start with the sulfate. We have 3 sulfates on the left. We only have 1 on the right, so we could very easily fix that by putting a 3 in front of the sulfate on the right. That gives us 3 sulfates on each side. When you do this approach, pretty much this tells you where you should go next, which would be the silver in this case. So I also have now 6 silvers on the right. That means I need to now go to the left and put a 6 in front of the silver. That fixes the silver, but again, now I need to go next to nitrate. I now get 6 nitrates, and I can fix that by going to the right and putting a 2 there. That gives me 6 nitrates. Also then gives me 2 iron, which is actually what I need anyways. So a lot of times it's a lot easier and a lot quicker if you have some polyatomic ions on both sides to sort of keep them together, start with those polyatomic ions and balance them as sort of whole units. You again can go element by element, but there's a lot more kind of multiplying in and multiplying out because of the polyatomic ions and the parentheses. Usually what will happen is very similar to what just happened there. At some point, everything else will just sort of fall into place if you sort of do it correctly. Any questions on that there? All right, so let's take a look at the next one, which is kind of a similar situation here. We got PB CO3 2 plus Ca NO3 2 gives us CaCO3 plus PB NO3 4. So same idea. I got a carbonate on the left and I got a carbonate on the right. I got a nitrate on the left and a nitrate on the right. So again, I'm going to kind of start with those polyatomic ions. And in this particular case, we'll start with the carbonate. Why not? So we got the carbonate that has 2 on the left, only 1 on the right. So to fix the carbonate, we would put a 2 in front of it. That now gives us 2 carbonates. And now gives me how many calciums? Also gives me 2. And again, that is where I should go next. So I would go to the left-hand side, put the 2 in front of the calcium. That now gives me the 2 calciums. And now in terms of my nitrate, it gives me 4 of them, which is good because that's exactly what I need on this side, which is 4. So I'm good there. And I obviously have 1 lead on each side. So it is done at that point. So you know, it's very easy sometimes to just sort of start with those polyatomic ions, keep them as whole units, and like I said, things will just sort of fall into place. Any questions on balancing in general? Okay. All right, so now we talked about balancing chemical equations. We're going to talk about ways to classify chemical reactions. And there are multiple ways at which we can classify chemical reactions. And there's really sort of two big classifications or umbrellas for which we can classify the same reaction a little bit more specific. The two big types of classifications are double displacement reactions and in a double displacement reaction, it has a general form of AB plus CD. These are both ionic compounds, so positive, negative guy, positive and negative guy. And what always happens in this case is the two positive guys switch partners. And as they switch partners, they will form new ionic compounds on the other side, like A and D plus C and B. So underneath double displacement reactions, which is sort of the big classification of reactions, you can more specifically classify those type of reactions as we will see, like precipitation reactions or acid-base reactions. The other big sort of umbrella is what we see right here, which is what is sometimes referred to as redox reactions. Redox reaction stands for oxidation reduction. And they basically involve electrons being transferred or an electron transfer occurring. As we will see, there really is three reasons why a chemical reaction takes place. The three reasons why a chemical reaction actually takes place, they're sometimes called driving forces for a chemical reaction, is basically an electron transfer, which we're going to talk about here, the formation of a precipitate or a solid, are really the formation of water. That in a nutshell is really why reactions take place. One of those three things are pretty much going to be happening in every reaction that occurs. Either electrons will be transferred, either you will make a solid or a precipitate, or you'll make water. All right, so up on top, like I said, these are the big sort of classifications, and we'll see a little bit more specific ways to classify. One thing that we will see in this reaction are the rest of this chapter here and this part of it is you can look at one reaction, and depending on what you're looking at, you can classify it in multiple ways, depending on what you're looking at. So let's start with redox type reactions. So when we talk about redox reactions, there's basically two things that occur. There is an oxidation that occurs, and when something goes through oxidation, it means that it loses electrons. And there's usually a reduction that occurs, which means somebody will gain electrons. Both of those things always occur together. So if something gets oxidized, something gets reduced, and vice versa. If somebody gets reduced, somebody gets oxidized. Some people remember that by Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining, whichever way you like. Use them both. Put Leo the lion on the oil rig and he goes grr, and you don't have to choose. But that's the way some people will remember it. So sometimes when you look at an equation, you might want to look at it and try to decide what is being oxidized, what is being reduced. And there's really sort of a simple way you could kind of do that. And it's like using like a number line of math, right? Somewhere there's zero. And usually to the right of zero are positive numbers, to the left of zero are negative numbers. When somebody loses electrons or becomes oxidized, Does that person become more positive or more negative if you lose electrons? You do become more positive, right? Because you technically have more protons than electrons. So if you find going from the reactant side of the equation to the product side of the equation, that particular substance is becoming more positive in terms of like its charge. It's really known as the oxidation state, but we'll call it a charge. This kind of charge is becoming more positive and is moving sort of in this direction. That means that thing is going through oxidation. When somebody gains electrons, they obviously are going to become more negative because they have just gained more electrons and have more electrons than protons. And that means that they would be moving in sort of the negative direction. And that thing is the thing that is going through reduction. So how do we determine that? Like I said, we really use what is truly what is known as the oxidation state, but you can sort of think of it as like the charge that's happening. So if we look at this reaction, which is up on top, which is sodium metal plus a little chlorine gas, makes some sodium chloride. When any element is by itself and really not combined with anything else, does it have a charge? So if I have just sodium metal by itself, it does not have a charge. Things really only get charges when like a metal and a non-metal come together, right? Make those ionic compounds. But if something is an element by itself, not combined with anything else, it has no charge or no oxidation state, which means that the sodium over here really has a zero charge or oxidation state. The chlorine is a diatomic molecule, an element. That's how it comes. Also uncombined would have a zero oxidation state. Now, when those two guys come together, it is at this point on the right-hand side when we make this ionic compound that the sodium now gains a +1 charge, like we know what sodium usually has, and the chloride gets a -1 charge because it is group 7. So by just simply looking what is happening for each of these things, why don't we start with the sodium here? When we look at the sodium, it is starting at 0 and it is ending at +1, which is moving in this direction, right? Which means the sodium is becoming more positive and it means the sodium is being oxidized, yeah? By the way, the beauty of redox reactions is as soon as you figure out that is the oxidized guy or the guy going through oxidation, by default, the other guy has to be going through reduction because they always occur together. So that's kind of the nice thing about it is if you could just figure out one of them, the other guy is doing the opposite thing. But we can even do it for our chlorine. Our chlorine is starting with 0 and it's ending at -1. It is moving in that direction, which is basically the reduction direction, and it is being reduced. Any questions on that? The more simple aspect of this is we always know that between a metal and a non-metal, when they come together, which one always loses electrons is the metal. It's always the one that will lose electrons. So when you have a metal and a non-metal together, the metal should always be the one being oxidized, and the non-metal should always be the one that is gaining electrons and being reduced in this case. So this is why this is what's referred to as a redox reaction, because what is essentially happening is the sodium is sending an electron over to the chlorine there, and that's where we have our transfer of electrons, which is really, again, why a reaction is taking place. Now, as we will see shortly, this type of reaction is also, although it is a redox reaction, can be classified as a synthesis or combination reaction. And that is when you basically take two things and you make one thing. And that's exactly what is happening in this reaction. We got a sodium and chlorine, two things that are coming together to make one thing. So this is what I was talking about a second ago. This sort of big classification of this particular reaction is a redox reaction. A more specific classification of this reaction is it's actually a combination or synthesis reaction that is taking place. Probably most people would call it synthesis or combination, but it is truly under the big umbrella of redox reaction happening. Any questions on that there? So if we look at this guy on the bottom here, we have magnesium plus oxygen makes a magnesium oxide. I don't know, that's a common experiment you sometimes do in lab. I don't know if you guys do it or not, but you like burn magnesium ribbon if you ever see it. Yes, are done. It's my favorite one. They go like observe what's happening, but don't watch the magnesium burning because you'll go blind. It's super, super bright. So if you do this, the magnesium by itself here is 0. The oxygen is by itself, which is 0. But when those two guys come together, our magnesium on the right there has a +2 charge. Our oxygen has a -2 charge. So again, if we just simply kind of use that number line, the magnesium is starting at 0, ending at +2, which means it is being oxidized as we would expect. The oxygen is starting at 0, ending at -2, which means it is being reduced in this case. So again here, this reaction could be classified under the big umbrella of redox. It also, as you can see as well, is basically two things that make one thing. Could also be classified as a synthesis or combination reaction as well because of that. Any questions on that there? Combination. All right, I think we will lay it up there for today.